Hi everyone. We're going to continue our work with differential equations today, and today we're going to solve differentiable equations. We're going to solve differential equations by separation of variables. Okay, we're going to talk about something called separable differential equations. So I want to remind you first of all what it means to solve a differential equation. A differential equation is when I give you an equation with a derivative. Okay, um, and when I ask you to solve it, really what I'm asking you to do is find the antiderivative. Well, we don't really have a way that we can find an antiderivative if we have multiple variables. If you look at these two examples here, there's multiple variables in there. These derivatives would have come from like an implicit differentiation situation. We did those at the beginning of the year. And so how do we reverse that process? Now, this process doesn't work on every differential equation in multiple variables. There are some other techniques that you'll learn later on down the road, probably not in this class, but you'll get to them. But there are certain types that can be solved using this method. And I've kind of got the process detailed out for you here. I think it'd be better if I just work through one first, and then we can come back up and look at the steps as they're written. Um, so what I'm going to do is I'm going to take this differential equation, I'm going to treat this dy and dx almost like they're their own variables, and like this thing is a fraction over here. And when I say separate, what I mean is get all the y's on one side and all the x's on the other. So if I want to move this dx to the other side, I'm going to multiply by dx on each side. By the way, all the movement we're going to be doing should be done with multiplication and division. We're never going to be adding and subtracting anything. Okay. Honestly, these first two steps could probably be done all at once, but I just want you to be really clear on what I'm doing here. 2xy squared times dx. Well, then I want the y squared over here, so I'm going to divide by that y squared. And I'm saying that I'm dividing by y squared. I think our life is going to be easier here in a second if I actually write this as 1 over y squared. Oh, messing with my color scheme here. Sorry about that. Uh, so 1 over y squared with the dy off to the side. And then over here, I have 2x dx. Okay, so I've got all my y's on one side, I've got all my x's on the other. I did all my movement using multiplication and division because that's how we want our things connected. And now what I'm going to do is I'm going to integrate both sides because that's ultimately what I want here. I want to be able to take an antiderivative. And if you look, if I put an integral sign here and an integral sign here, now I can do this because this is telling me integrate in terms of y, and this is telling me integrate in terms of x. So I need to have the dy and the dx in the correct places before I'm allowed to do that. But now I can do an antiderivative on both sides. So my antiderivative of 1 over y squared, remember I'm thinking about this as y to the negative 2 power, okay? So y to the negative 2 power, I'm going to add 1 and make it a y to the negative 1. Let's see, I'm just digging for a different color pen here. So this is going to be y to the negative 1 power, and then divide by that negative 1. So really, I'm going to have a negative in front here. My 2x is going to become an x squared. And then technically, both of these should have a plus c on them. Want to make it super clear. Actually, maybe I'll do this off to the side. I don't think you have to write this down. But let's say that I have like well, what is this one right now? Negative 1 over y plus c equals x squared plus, and I guess I should make this like c1 and c2 because those don't have to necessarily be the same numbers, right? So that's technically what I have going on right now. The first step I would probably take here is to subtract this over here, and so it would become negative 1 over y equals x squared plus, and then this would be c2 minus c1, like I would put those together. Well, these are just constants, and I don't even know what these constant values are yet. So realistically, I can just lump all of this together and say, I'm just going to call this whole thing some other constant. I'm just going to call this C. So that's why we can get away with only putting it on one side, because it's like essentially we're pretending that We just already moved all the c's together to the one side of the equation. So I usually find it easiest, like I said, to put that c on the side with the x. Okay. And now I have my solution. I have to dig for it a little more to get it in the format that I want. But this thing that's written here in blue, that is my antiderivative, right? I like that. I do want to point out that if I had an initial value, this would be the time that I would want to plug in and solve for it, because I'm going to do some rearranging here in a second. So I'm going to just kind of do something that might not make sense to you right now, but I'm going to kind of show, like, if I were solving for C, if I had like a coordinate to plug in, I would do it right now, okay, with the equation in this form. I don't have that. So this is me kind of skipping that step. This gap represents like that other step that I would normally take. And now I'm going to take this thing. I'm going to rewrite this as -1 over y equals x squared plus c. Let's see. So now I'm trying to solve for y. That's my goal here. And I think with this one, probably the easiest way, I mean, I could multiply by y on both sides. I think I'm just going to say, hey, let's flip this side around, which means I'm going to take this thing over 1 and flip this side around. I can do that. Okay, I can flip both. So I'm going to make this a -y equals 1 over x squared plus c. And then I'm going to essentially multiply by a -1, right? So I'm going to multiply by a negative, I'm going to multiply by a negative, and I'm going to end up with this equation. Y equals -1 over x squared plus c. And that's my antiderivative. Now, um, sometimes I am going to have like an initial value, like I mentioned a second ago, where I can figure out what C is. I didn't have that here. So that's what I would normally do here. And then I would have had a number here to work with and simplify and all of that. But the idea is, if you look at the steps I gave you, rearrange the equation, okay, so that all y's are on one side, all x's are on the other. Integrate both sides, put the plus C with the x, okay? Um, Plug in initial condition if given. So that's again what would have gone here kind of in the middle, and then solve for y. Okay. And so sometimes you'll have a number in place of that c. Sometimes it just stays a c all the way throughout. But that's my antiderivative right there. Okay. Okay. So let's look at problem number 2. I've got dw over dt equals 2t 1 plus w squared. Remember, I'm moving everything in terms of multiplying and dividing. So I want to take this thing and move it this way, and I want to take the dt and move it that way. Okay, and I'm going to try to do this all in one step. This side is going to become a 1 over 1 plus w squared, okay, um, times dw. This other side is going to become a 2t times dt. So I've got t's on one side, w's on the other. And then I'm going to integrate. Okay, so the question is, what's the integral of this thing? What's the antiderivative of this thing? Hopefully you recognize that as an arctan. That's an arctan of w. And this side is going to become a t squared. In this scenario, with that t on the bottom, just like my x is normally on the bottom, this is my independent variable, so we're going to be solving for w here, like we want a w equals type equation. So I'm going to put my plus c over here. Normally, I would stop right here and solve for whatever c is equal to, but I'm not going to. Now I have to think about how to get w back by itself. So let me just rewrite my new equation here. So tan -1 of w equals t squared plus c. So how do we undo an arctan? Well, I would undo an arctan with a regular tan. Okay, the tangent of tan inverse is going to cancel itself out. So this is now going to have a tangent on it. This and this cancel. And now what I have is w is equal to the tangent of t squared plus c. And that's my solution to my differential equation. Okay, let's do a couple where we have to solve for C. And now would be a good time to maybe pause the video and maybe try that first step on your own, where you get the y's with the y's and x's with the x's. I do want to point out this process doesn't work for every differential equation. I'm not sure if I said that at the beginning of the video or not. What you're really looking for are places where you have like y's diagonal from y's and x's diagonal from x's, because that makes your cross multiplying really easy. Okay, and that's essentially what I'm doing is I'm like multiplying by the y over here, I'm multiplying by the dx over here. So now I'm going to have um, y dy equals x plus 1. This should be in parentheses so that you're not just multiplying the dx by the 1 at the end. I'm going to throw an integral in front of both. Okay. And now let's actually integrate. So the integral of y would be 1/2 y squared. The integral of x squared plus, I'm sorry, x plus 1 would be 1/2 x squared plus x, and then we get our plus c in there. Now, I do know some people like to solve for this y first and then plug in their initial condition. There's some weird things that happen, and I'm sure we'll run into some of these mistakes and things like that. But there's some weird things that happen sometimes when you put the numbers in later rather than earlier, like some of your simplifying that you do changes the relationship of that c value. So that's why I would always suggest doing that right now, like before we move any further. I'm going to keep my 1/2, and then I'm going to plug in my y value, which is the 2, equals, and then let's see, 1/2 times 1 squared plus 1. These are, I'm pulling my x in right here, plus c. So let's see, that's half of 4, so that's 2. And this is half of 1 plus 1, so that's 1.5 plus c. And so then 0.5 must be my c value. So now I'm going to go back over here and start with that equation. I'm going to start with 1/2 y squared equals 1/2 x squared plus x plus 1/2, or 0.5. Okay. And my mission now, and I'm sorry that's kind of crammed in over there, but my mission is to solve for that y value. So probably the first thing I would do is go ahead and multiply everything by 2 to get rid of that 1/2. So now I'm going to have just a plain old y, I'm sorry, a y squared, equals, now this will be a 1x squared plus a 2x plus a 1. And then I'm going to take a square root, and I'm going to say y equals. Now, there's something we have to be careful of with our square roots. Remember, when you're solving equations and you take a square root, there can be a plus or a minus. So I'm going to say plus or minus square root of x squared plus 2x plus 1. Okay. And really what I want to figure out here is which one is it. I need to commit to one of these. It's got to be either the positive or the negative. Okay. Look at my initial condition, right? This is saying when I plug a positive number in, I'm getting a positive number out. Okay. If I'm plugging in a positive and I'm getting a positive answer, then there's no way this could have a negative sign sitting in front of it, right? So this should be the positive version of this equation. And so my final answer here, my solution to the differential equation, would be the positive square root of x squared plus 2x plus 1. Okay. Now, if this was a situation where f of 1 was -2, let's say, the only way that could happen is if this square root actually had a negative in front of it, right? Because you can't get a negative answer out here. So we would have to have the negative version of that plus or minus. Okay. Onward. Let's try one more. So this one's a little bit trickier in terms of how to solve it. It's a little bit ugly. I'm going to do kind of the same thing. I'm going to multiply by the 2a over here. I'm going to multiply by the 2 or the db over here. Sorry, that might have just made a mess of things. So what I really have now is 2a dA equals, and then over here I have 5 over b plus 1 db. And let's integrate. So integrate. Antiderivative of 2a would be a squared. Um, Antiderivative here should be 5 natural log of b plus 1. And then we get a plus c. I'm given that a of 0 equals 3. So this is my input, this is my output. Okay. So this is my a value, this is my b value, this is my input, which is the b. Okay. So I'm going to solve for that real quick. I'm going to solve for that c value. My a squared, so that's 3 squared, equals 5 natural log of 0 plus 1 plus c. Okay, so 9 equals, now careful here, this is 5 times natural log of 1 plus c, but natural log of 1 is just 0. So really this whole thing goes away and we just get that my c value is 9. Okay, so I'll go down here so that I'm not so cramped this time. Now I'm going to take this 9, I'm going to put it right over here. And so now my equation is a squared equals 5 natural log b plus 1 plus 9. And then I just need to solve for what a is equal to, which means I'm taking a square root of all that. Okay. Again, technically this would be a plus or minus all of this square root, so 5 natural log of b plus 1 plus 9. And I want to think about, should it be the plus or the minus? Well, when I plug a 0 in here, I'm getting out a positive 3, not a negative 3, right? So that means I'm choosing the positive version. I promise sometimes this does happen where it comes out as the negative, so we want to be careful about that. That's why I'm trying to drive this home. Um, so my final answer here would be the positive version of this. 5. And by the way, if you don't want to write it twice, you don't have to. I just kind of write it that way so you can make sure you're thinking about it. And that there, my friends, is the antiderivative. Okay. So that's really all there is to this. It's integrate both sides after you've got the variables separated. Solve for C if you can, and then solve for your for your dependent variable. So whatever your y is supposed to be. And if you're ever confused about which one is your y, remember that usually we write derivatives dy over dx. So whatever this top variable is, it's a pretty safe bet that that's the one you're solving for down here. Okay. So that's all there is to that. As always, let me know if you have questions when we talk about this in class.